Next up, we've got the life cycle of stars, and once again, these are revision videos, so it's only the absolute basics that we're going to cover here, I'm afraid. Okay, so here we go, and we're going to have keywords for you to mention in these bubbles round the side. Right, all stars start out life in a nebula, and so nebulae are often called stellar nurseries. It's where stars are born. So a nebula is a cloud of dust and gas. And dust and gas particles, they don't have very much mass, and so they don't exert very big gravitational forces on each other, but they do exert gravitational forces on each other. And so very, very slowly, these dust and gas particles pull each other together. And so your nebula, your big cloud, starts to get these clumps in it. And each clump is eventually going to become a star. So as a clump of dust and gas keeps pulling together, its pressure increases and that makes its temperature go up. And so it'll start to glow, but there's no fusion happening yet. So it's not a proper star yet. For you to get fusion happening, you need to have gravity keep pulling it together until the pressure and the temperature get very high. And that's because at very high pressures and temperatures, the particles are hitting each other at very high speed. And you need that to get the protons close enough together to make them stick together. Why don't they want to stick together otherwise? Because protons are positively charged and so they repel each other. So they have to be moving really quickly in order to get close enough together that they can overcome the electrostatic repulsion. That's what we say. Okay, and but when they do, then fusion starts and you're in now a main sequence star. The star has been born and it's going to be hydrogen fusing into helium. Important thing to note here is what decides the size of the star. So you've still got gravity pulling all of the particles in the star together, trying to collapse the star. And so why doesn't it collapse? Because in the other direction, pushing outwards, you've got the force due to gas pressure. So that's just these particles flying around really quickly and exerting a pressure that way. And you've also got radiation pressure, which is not something you've heard about at GCSE. So radiation pressure, photons of light have momentum, and that means they can exert forces and they can exert pressure. And so you also have the pressure outwards from the radiation coming out of the star. Okay, I'm simplifying a bit now because actually you've got the core of the star and then you've got the outer layers of the star. So we're going to be simplifying a little bit here. But basically, when the hydrogen runs out, the fusion reaction in the centre stops and that removes the radiation pressure. And so now it's not balanced anymore. The inward force is bigger and the star collapses. Because the inside of the star has now collapsed to a really small, a much smaller thing, the outside layers of the star don't feel as much gravitational force inwards, and so the outer layers actually drift off at that point, and that's why the star gets bigger. You think it's going to get smaller, but it gets bigger overall because the outer layers have drifted outwards. This makes them cool down as well, and so they are going to only be red as opposed to yellow or orange or whatever colour the star was before. And so now we're going to turn into either a red giant or a red supergiant. Now, what decides whether a main sequence star becomes a red giant or a red supergiant is its mass. If the star has a mass of less than 1.4 solar masses. Now this weird symbol here, this M with the circle and the dot in, that stands for the mass of our sun. So if a star has less than 1.4 times the mass of our sun, it's going to turn into a red giant. Otherwise, if it's bigger than that, it's going to turn into a red supergiant. Now once again, we're simplifying a lot here, but basically the red giant, it has enough mass to fuse helium nuclei into carbon nuclei, but it doesn't have enough mass. It can't make a big enough pressure and temperature to fuse anything bigger. But the red supergiant has got enough mass to keep fusing these larger and larger nuclei. Okay, so it's all over now for the red giant because it just doesn't have enough mass to do any more fusion. And so although it has collapsed, so we've taken away, the fusion has stopped, so we've taken away the radiation pressure, and now the inwards and outwards forces are not balanced, and the star has collapsed again. But it still can't, even that is not going to make it hot enough or having high enough pressure for fusion to start again. And so you just end up with this very hot, very dense core of the old star gradually cooling down, and that's your white dwarf. The outer layers, when the star collapsed again, remember the outer layers don't feel as much gravity, and so the outer layers drift off to form a planetary nebula. This is a misnomer. It's not. It hasn't got anything to do with planets. It does just mean a nebula that has been created by the outer layers that drift off the core. If, however, you were a red giant, then when you've finished fusing, and iron is your limit there, when you can't fuse anything heavier, then again fusion finishes, the radiation pressure goes away, the inward force is bigger than the outward force, and the star collapses. And this is a massive collapse, which causes a huge increase in pressure and temperature very, very quickly. And for fascinating reasons we're not going to go into, this causes a supernova, which is a massive short-lived explosion. Supernovae, the flashes you get in the sky are so bright that they're like documented through history, hundreds and hundreds of years ago. These things were so notable that they got written down in ancient records. So also the temperatures and pressures that you get in a supernova are massive, and that means that there's enough energy available to fuse heavy elements even heavier than iron. And in nuclear, we'll talk more about that. And then, once again, two possibilities. If your mass is bigger than 2.5 solar masses, then you're going to turn into a black hole. You are then a singularity. You have no volume, but a huge mass. And for a long time they thought these things couldn't possibly exist, and they were all very upset about them, and now we know that they do, and in fact probably most galaxies have got one at the middle of them. But if you have less than 2.5 solar masses, then instead you're going to become a neutron star, and we're going to talk more in the next video about what's going on when that happens. And if you're a neutron star, you are now extremely dense. I can't remember, I meant to look it up, but look up what a teaspoon of what's the mass of a teaspoon of neutron star, because it's ridiculously huge. And you are in fact made entirely of neutrons. Okay, lots of questions on the life cycle of stars ask you to describe some part of this, but I thought that number 4 here was it was a bit more unusual, so have a go at number 4. Okay, so quite a good one, this one, I thought. The very first stars, remember, were made from these atoms, and these atoms are lighter ones. It's like hydrogen, helium, lithium. These are the smaller atoms that get made first, whereas the later stars are made from planetary nebulae, and also stuff that gets that drifts off or gets chucked out in a supernova. So later stars, younger stars like our sun, are made of the leftovers of earlier stars. That's the key thing. So the very early stars are just made of the lighter elements like hydrogen and helium, but the younger stars like our sun are made of the heavier elements, and that's because they're made from the leftovers of earlier stars, which made those heavier elements in them during fusion.